This is the Chapter 10, Segment 1 YouTube outline. The vertebrate eye acts in some ways like a camera. The eye has optical functions and neural functions. The optical functions are capturing light and forming detailed spatial images. Neural functions, transducing light into neural signals and then processing those signals. To produce an optical image, the eye has many features of a camera. The cornea and lens focus light, and the cornea bends light rays and is primarily responsible for forming the image of the retina. This bending of light rays, called refraction, is the basis of such instruments as eyeglasses, telescopes, and microscopes use. The ciliary muscle, one of the muscles that controls the shape of the lens inside the eye, focusing the image of the retina. The amount of light that enters the eye is controlled by the size of the pupil, which is an opening of a colorful disc called the iris. Dilation of the pupil is controlled by the sympathetic division of the autonomic nervous system, and constriction is controlled by the parasympathetic division. The movement of the eyes is controlled by the extraocular muscles, three pairs of muscles that extend to the outside of the eyeball to the bony socket of the eye, known as the orbit. The visual processing begins at the retina. The first stages of visual processing occur in the retina, the receptor surface inside the back of the eye. The receptor cells that detect light are called photoreceptors. There are two kinds of photoreceptors, rods and cones. Both receptors release neurotransmitter molecules that control the activity of the bipolar cells that synapse with them. The bipolar cell, in turn, connects with the ganglion cells. The axons of the ganglion cells form an optic nerve which carries information from the eyes to the brain. Horizontal cells make contacts among receptor cells and bipolar cells, and amacrine cells contact both bipolar and ganglion cells. Rods, cones, bipolar cells, and horizontal cells generate only graded local potentials. They do not produce action potentials. Ganglion cells do produce action potentials. The scotopic system, only one receptor type, which are the rods, and therefore does not respond differently to different colors. A lot of convergence as many rods provide information to each ganglion cell, and this involves low levels of light. The phototopic system involves high amount of light, and it uses cones, and has less convergence as some ganglion cells report information to each ganglion cell. Photoreceptors transduce light into chemical reactions. The light changes the retinal shape to forming the rhodospin photopigment rods that respond to light to activate almost 500 molecules of G protein transducin. This activation causes GTP molecule to replace GDP molecule bound to transducin. The activated transducin activates phosphodiesterase molecules. Each PDE molecule hydrolyzes almost 2,000 molecules of cGMP, reducing its concentration. The reduction of cGMP leads to closures of Na channels and hyperpolarization of the receptor. One photon of light can block the entry of more than 1 million sodium molecules. The cascade process required to stimulate the visual receptors helps to account for three characteristics of the visual system. One is its sensitivity, because the weak stimuli are amplified to produce physiological effects. The integration of the stimulus over time, which makes vision relatively slow but increases its sensitivity. And the adaptation of the visual system to a wide range of light intensities. So what is photoreceptor adaptation? That is the tendency of rods and cones to adjust their light sensitivity to match ambient levels of illumination. Two main factors. The most important factor is one shared by the sensory modalities, varying the concentration of calcium ions. Photoreceptors regulate and release stores of intercellular calcium ions to control the sensitivity to light. Another is when the photoreceptor pigment is split apart from the light and its two components, the retinal and the ospin, then they recombine slowly. Acuity is the best focal vision. The vision field is the whole area you can see without moving your eyes or head. Visual acuity is the sharpness of vision, especially fine in the center of the visual field, and falls off rapidly toward to periphery. The central region called the fovea has a dense concentration of cones. Figure 10.6. In the fovea, the light reaches the cones without having to pass through blood vessels and other layers, from the ganglion cells that are bipolar to the photoreceptor cells. Quick movement of the eye, called saccades, bring various parts of visual scene to the fovea to take advantage of the sharp visual acuity there. The rods are distributed differently than cones. Rods are absent in the fovea, but more numerous than cones in the periphery of the retina. And that concludes my Chapter 10, Segment 1 outline.